Okay, so I see that we are at the top of the hour. We're going to start slowly while the last person are joining. So good morning, good afternoon, and good evening, everyone. My name is Jebelech. I am one of the Program Organizing Committee chairs, and welcome to IPPW 2021, Session 4, dedicated to innovative concepts for exploration. I wanted to go over some rules with you and some information before I hand it over to the session chairs. Firstly, all the content that will be presented today is getting archived and will also be available on the International Planetary Probe Workshop YouTube channel within a week. If you go there, you will already see session 1, 2, and 3 already uploaded, along with the different poster presentations. Secondly, the meeting itself is also recorded, and it will be available in the previously mentioned platforms. Finally, please do not unmute yourself during the webinar. All the questions that you will have, please address them through the chat box. We will be moderating the mics, and we will be kicking any person that insists too much in making themselves audible. And with that, I will wish you to have a great session. And now, please, I will pass it to Dimitri, Robert, and Alena.
Thank you, Jill. This is Robert Dillman at NASA Langley. And like Jill said, good morning, good afternoon, and good evening to everyone, depending where you are. We've got an exciting series of presentations lined up for you today. And as was mentioned, we ask you to submit questions through the chat window. And we'll be, to help stay on schedule, we'll be reminding the speakers when they have about 2 minutes left in their time slot. We're starting today with our invited speaker, after which we'll have 5 minutes for questions. Athena is Director of Research with the French Center for Scientific Research, based at Paris Observatory. She specializes in planetology. She contributes to the development of space missions and analyzes the required data to investigate the atmospheres and surfaces of planets, satellites, and exoplanets. In particular, she is a self-described Titan fanatic, and she has extensively worked on Cassini-Huygens data. She is currently the chair of the European Space Agency's Human Exploration and Science Advisory Committee and of the COSPAR panel on planetary protection. She is also a member of several other international advisory bodies. She is currently contributing to the upcoming JUICE mission to the Jovian system and the Ariel mission to the exoplanets, while awaiting for the next chance to revisit the Saturn system. Take it away, Athena.
Okay, thank you very much, Robert. Hello, everybody. I hope you can hear me and see me okay. Pleasure to be here today, and many thanks to the organizers for giving me this opportunity to talk to you today. It is my pleasure also because this is, I think, part of the lecture for the Al-Sif Memorial Award that I received in 2019, and I'd like to thank the people here from the IOC, IPPW committee and the Al-Sif committee that we've worked together for many years. I saw Raj was here, and I also saw Bernie and some others. Thank you for attending and letting me give this keynote. So I just wanted to say a few words about a lifetime, or at least a career time quest that I have to better understand a favorite object of mine, and you heard it right now from Robert in the solar system, and that is Titan, which I had the pleasure to explore by using probably all available means in observing techniques and modeling, but also specifically for space observations. I used all kinds of elements, orbiters, probes, landers, and balloons. And in the following talks in this session I saw, which is very interesting today, you'll hear more about some of that, like aerocapture. I saw melting and hopping probes, heat shields, seismometers, and more. And I just wanted to emphasize that all of these ideas have been suggested or applied to Titan at one time or another. So you can imagine that the quest for better understanding this fascinating world has engaged many people and warranted a series of space and ground-based investigations over a very long period of time, and it is far from finished. So next, please, team. But for me, I just wanted to say that all started somehow in 1980 when, although I didn't witness it myself, I got my first flyby, and that was the one by Voyager 1 at Titan on November 12, 1980. And this flyby afforded us some data and the characteristics that are shown up here on the top of the slide. And all of that significantly increased the interest of the scientific community for its investigation, in particular for its Earth-like atmosphere, because we couldn't see the surface through the thick clouds with the Voyager cameras. So I did my PhD on something like 300 Voyager 1 IRIS spectra. IRIS was the infrared spectrometer on Voyager, which preceded Cassini-Sears. And so I analyzed about 10 years after the flyby that data with a radiative transfer code that I had developed to infer the thermal and chemical structure of Titan at different locations during what was at the time the early northern spring. And this is what you see here at the bottom left, compared to what we actually got with Cassini 25 years later during northern winter, about which I'll talk a bit more later. So my PhD on Titan 1989 made me a sort of an expert in Titan already at that time, Titan Matters, and led to my inclusion in the team of 4 proposals for the Cassini-Huygens mission, which was being developed at the time, of which 3 were selected to fly, much to my amazement, I have to say. So next, I wanted to talk to the fact that Voyager, with just one flyby, still provided us with most of the knowledge we had about Titan before Cassini, about the composition that you see here. You all know that it's essentially nitrogen and methane, and that forms the hydrocarbons and the nitriles and the prebiotic chemistry that we have in the atmosphere, and a little bit of oxygen. And so, more importantly, Voyager pointed to many things that we didn't know, like the methane cycle, exactly how it was operating and parallel to what we have on the Earth, the properties of the surface and the internal structure and more. And all of these unknowns we transformed into the set of arguments that helped us defend a proposal for a large mission to the Saturnian system and Titan in particular with the space agencies in the early 90s. So next you'll see that when the proposal became the Cassini-Huygens mission, the name was given for 2 men dear to my heart who studied the Saturnian system in the 17th century. One of them is Giovanni Domenico Cassini, who was an Italian-French director in Paris Observatory. And you can see him here to the bottom left, where he observes Saturn from what is the Paris Observatory and where I work today. And obviously, Christian Huygens, you all know, discovered Titan. And you can see here also at the bottom how he explained the observed aspects of Saturn in the Systema Saturnium in 1659. Next, please. So indeed, it all started in the 17th century with Cassini and Huygens. Can you click again, please, Tim? But you see here, but it was promoted actually and brought to fruition in the 90s with people like Toby Owen and Daniel Gauthier, whom you see here, but also Wingate, Michel Combs, many, many others who worked hard in getting the Cassini-Huygens mission selected, developed, optimized, and launched. Next slide actually shows that the mission was selected, and during the development of Cassini-Huygens, you can see here that many models were developed for things we didn't know, like the surface with Lunin's exciting model that showed very much something like what we found in the end in 1990, and Wilson's and Atreya chemistry. But also you can see also some photos of teams gathering to prepare the mission. Up left is the Huygens Atmospheric Structure Instrument team in Canterbury, where Marcello Fucchignoni and John Zarnecki for the surface science package in the front, and some people in the back were preparing those instruments. You can probably identify some of them, and young Ralph Lorenz at the far right, and me in the middle to help with diversity, I think, and parity issues. So then Cassini was launched on 15th October 1997 from Cape Canaveral, and you see here some very happy faces from Paris Observatory at Cape Canaveral at the time, and I had a great pleasure and privilege to attend that launch. So next is the fact that I just wanted to stress that during the long 7.5 years, almost a season on Titan trip that Cassini undertook, we didn't just sit and wait. So you can see we were desperately trying to see what was under Titan's clouds, and we used different methods in spectroscopy where we detected the water vapor in the atmosphere and benzene, but also using the HSD with Peter Smith's team at the time and adaptive optics in many telescopes on the ground that gave us some information about the surface, and in particular the bright and dark regions that we would better explore with Cassini later on. So next is Cassini on its route to Saturn, and you can see here the trajectory with flybys of Venus, the Earth, a flyby of Jupiter in 2000 at the same time as the Galileo mission was there, and the Saturn orbit insertion depiction here in July 2004. Next is to say a few words about the Cassini spacecraft, which was one of the largest, heaviest, and most complex interplanetary spacecraft ever built at the time, with two elements on board, the Cassini orbiter and the Huygens probe. And besides the traditional elements and instruments, there were several novelties with a large array of powerful instruments and cameras, and the spacecraft had also the capability to take accurate measurements and detailed images in a variety of atmospheric conditions and geometries. And the spacecraft communicated with Earth through its antenna subsystem that was also used to shield the instruments and also for some scientific experiments. And it had 3 radioisotopes, RTGs actually on board for the spacecraft, and the probe was powered with 5 lithium batteries to support the electric system. So next is just a few words that I want to say about the people in this endeavor. Because NASA and ESA partnered with the Italian Space Agency and many other international teams that came on board. And this is the top list of people involved in the mission, with the PIs, the IDSs, and of course the mission managers and project managers, some of whom retired and were replaced later on. And in red here, I've highlighted 2 instruments of the orbiter that offered the data I worked most on as a COI, and that's the SEERS instrument and the VIMS instrument. And the picture here shows some of the members of the Cassini mission at a JPL meeting in June 2017 before the end of the mission. And more than 5,000 people, I'm told, worked on this fantastic mission. So next is a slide that speaks to the probe Huygens, on which we had 6 instruments. And you can see here the PIs and those instruments along with the teams. And these were essentially experimenters because we had never done this before. And even today, Huygens is the probe having landed the furthest in the solar system. And all of these people did a fantastic work with these instruments. And I'll talk more about Huygens in what follows, because this is IPPW. And the HAZI and DSR instruments where I was a COI. But I just wanted to say that this payload was a fantastic precursor to the whole series of future instrument suites on other missions that always proved reliable and efficient. So next is the scientific objectives that we had at the time for Titan that were obviously numerous, as we didn't know much about the satellite. But the science goals you see here included atmospheric composition, circulation, surface properties, and more. And I will not attempt by any means to describe all the results of the Cassini-Huygens mission. It's not the purpose here. And it would probably take me more than 3 days. But I just wanted to highlight a few aspects that were important to me and gave me the insight to propose future concepts to continue the exploration. So next is that something that you've seen probably many times, where there's a lot to be said for the discoveries of 2 amazing worlds that we got for the price of 1, because also Enceladus, as you know, we discovered first with the magnetometer and then with other instruments the geysers that emanate from the South Pole region, spewing water and organics. And those geysers were actually also explored in situ thanks to an orbiter passing through them at a distance as low as, I think, 25 kilometers from the surface of Enceladus. And Titan obviously demonstrated that it was far more interesting than anything we had imagined before. And none of us had predicted the channels, the dunes, the lakes, all of those terrestrial features, but composed of different materials than on Earth on its surface, or the meteorological phenomena in the atmosphere that we found on the satellite, thanks to a combination of measurements by all the instruments, and in particular shown here by the ISS cameras and some of the probe's instruments close up. So next shows one of the aspects that got a lot of attention from the community, and this is, as you all know probably, the atmosphere and the organic chemistry within it, as was studied by different instruments at different altitudes, with the discovery of high molecular weight species present in the ionosphere by the INMS, complemented by measurements in the stratosphere by SEERS, and then the gas chromatograph mass spectrometer, GCMS, that made compositional detections in the troposphere and during the descent at the equator of Titan and on the surface. So I worked in particular on the spectra acquired by SEERS, as I said before. And if we can go to the next slide, you'll show that the data that we got from SEERS allowed us to determine the changes in Titan's atmospheric composition and thermal structure. And those space observations were complemented by ground-based discoveries and also by ISO observations that I mentioned before. So one Titan year, as it follows Saturn around the Sun, lasts about 30 terrestrial years. And Cassini covered 2 seasons during its 13-year mission. The northern winter and northern spring that showed dramatic changes in chemical content and temperature in the atmosphere. And one fun thing I did in 2010, when it was one Titan year since the Voyager 1 flyby, was to attempt to combine all the data from Voyager and ISO and the first data from SEERS to see if I could describe the whole Titanian year from the atmosphere point of view. So it shows that we do need to explore more Titan, more at the same season, but also perhaps one day at a different season. And in what follows, I'll focus on Huygens. And the next slide, for instance, shows that the descent of the probe through Titan's atmosphere with the use of the 3 different parachutes. And you all know how successful that was. And the landing on the surface was soft, and no damage was suffered by the probe. And amazingly enough, all 5 batteries on Huygens were operational. And the surface phase of the mission lasted 1 hour and 12 minutes, considerably longer than what we had anticipated. And Huygens and Cassini communicated to relay data until Cassini orbiter fell off the horizon. And the probe continued to acquire data, and very large radio telescopes on Earth were also listening to Huygens's 10-watt transmission using the technique of very long baseline interferometry and aperture synthesis mode, which proved very helpful also for the Doppler wind experiment. And early indications when we landed on the surface were that Titan surface consisted of a thin frozen crust that is around 10 centimeters thick with a less dense layer beneath. And John Zarnecki called that a crème brûlée. So that was a fun time to follow. As you can see in the next slide, where you can see us all on January 14, 2005 at the ESA Operations Center in Darmstadt in Germany. And you can see us all here on the right hand, worried and somewhat perplexed, wondering what is going on, until we figured out how the probe was rotating, which escaped us in the beginning. And then you can see the happy faces after we figured all of that out. And to the left, you have Bob Mitchell, the NASA Cassini program manager, Jean-Pierre Le Breton, and myself celebrating the 5th anniversary of this wonderful landing 5 years later in 2010 in Spain. So next slide highlights some of the issues that I wanted to touch upon that we faced with Huygens and had to indeed do some figuring out. It concerned the trajectory of the probe and the data acquisition. And of course, you know that some corrections to the trajectory had to be applied because there was a communication design flaw that would have caused the loss of all data transmitted by Huygens. But in the end, Huygens detached a month later than originally planned and approached Titan in such a way that its transmissions traveled perpendicular to its direction of motion relative to Cassini. So that reduced a Doppler shift, and the data transmission succeeded, although the information from one of the two radio channels, A channel of A and B, was lost due to a software design error, where channel A's receiver on the orbiter was never commanded to turn on. But because channel A was not used, we lost something like half of the 700 images that were expected, and some all Doppler radio measurements between Cassini and Huygens were lost as well. But in the end, the wind profile for the experiment was recovered thanks to the fact that Titan's weak signal was captured by Earth-based radio telescopes, as I said before, and maybe they were not as accurate as with Cassini, but we still got that, and we got an estimate of the wind profile, and the wind speed on the surface was estimated to be between 0.3 and 1 meter per second. So next slide shows some of the results we got with HAZY, the Huygens Atmospheric Structure Instrument, where we studied the physical properties of Titan's atmosphere during the entry and descent phase and at the surface. And it measured the atmospheric deceleration, pressure, temperature, and electrical conductivity, ion conductivity, acoustic noise, and radar echoes below 60 kilometers in altitude. And also it was the first time in history that audible sounds from another planetary body had been recorded. And Marcello and everybody on the HAZY team will use this recording and played the sounds of the probe descending through Titan's atmosphere. Next slide, it talks to the descent imager, spectrometer, radiometer, which was developed at the Lunar and Planetary Laboratory at the University of Arizona under the direction of Martin Damasco. And it was an extraordinary instrument, and we had great fun exploring the methane absorption, the aerosols during the descent, and the surface properties also that proved to us that the absorption coefficients, for instance, for methane that we had at hand at the time are different from what we find in laboratory measurements, and we're currently trying to improve all that. And also notable is that the reflectivity recorded by DSR cannot be reproduced by ice and organic mixtures in the laboratory even today. And the next slide shows actually the spectacular images taken with DSR's cameras showing the landing site, which is reminiscent of a dried up riverbed with rounded pebbles, a few centimeters in diameter, probably made of water ice resting on a darker granular substrate. But if you can click again, team, please, I would like to just say that in other DISR images from higher altitudes, one can see a clear plateau with a large number of channels cut into it and drainage networks. And from the orbiter, you can see here on the left, with data from the Cassini radar, we get the context underlining that's the importance of getting different resolutions and different perspectives, both from in situ and remote observations. So the next slide says that all of these observations and with the instruments that we had on board of the mission, we managed to achieve very many science objectives at Titan that were more or less planned, but also technological amazing breakthroughs. One extra finding of great importance is the dense, salty global ocean in Titan's interior, deduced from gravity measurements and sandwiched between two ice layers. But unfortunately, next slide tells you that the Cassini mission, although it lasted longer than we hoped for at the beginning, ended in 2017 after an amazing grand finale that crashed the spacecraft into Saturn's atmosphere. And so you can see that if you can click again, team, that we're saying goodbye to the mission on 15 September 2017. In particular, you can see Mike Flaser and the Sears team there, and us reporting back to our home countries. And this mission, if I judge by my own experience with Voyager, will provide work for at least 2 next generations of astronomers. So great mission. The next slide says that the heritage that we got from this Cassini mission is that Titan is a fascinating object, so that the quest could not stop there, because we really need to investigate more the physical conditions, the undersurface, water, ocean, climatology, seasonal effects. All of that requires, you can see how complex the system is, and all of that has become evident. And the next slide says that Titan is a unique world because it sits actually at an intersection between ocean worlds with a fixed subsurface ocean, but also it is very much close to terrestrial world that we need to further investigate, in particular for the habitability potential of the ocean. And we also will need to determine its internal structure and physical processes. And as I said, the next slide speaks to the fact that the methane photolysis in Titan's upper atmosphere, which drives an organic chemical factory on the satellite, is something that would teach us a lot for the early Earth, the conditions on early Earth, but also on the present day Earth. So next slide just is fascinating to show how our view of Titan has changed in 35 years. You can see we went from Voyager to Cassini with a ground-based measurement. So what is next? Next is the next slide, where you can see that from as early as a couple of years after the arrival of Cassini-Huygens, and in almost all of the calls from ESA and NASA, there have been numerous proposals to return to the Saturnian system and explore with innovative concepts. But Aviator, JET, TAE, TIME, and others that I'm undoubtedly forgetting some of them, those proposed by 2017, opened the way for further innovative investigations of Titan and Enceladus. And I took part in some of these efforts. If you can click again, please, team. And in particular, the TSSM mission that you see here, about which I'll say a few more words. And the recently proposed Explorer of Enceladus and Titan mission to ESA in the M5 Cosmic Vision call that included a solar electric spacecraft with a large instrument suite and lake probe and a radar system. So the TSSM mission, if you can click again, please, team, is a study that took place in 2008-2009 with a coordination by the people you see here, Jonathan Lemine, Dennis Matson, Jean-Pierre Le Breton, Kim Ray, Christian Erd, and many more, a huge international team. And it was in the framework of delivering two large missions to the agencies, one for the Jupiter system and one for the Saturnian system. And you can find the reports of those two missions on the NASA and ESA website. But the next slide comes to TSSM in particular and shows that the mission had important goals that you see here, touching a wide range of planetary science disciplines and aiming at a better understanding of Titan as an Earth-like world with a unique prebiotic chemistry, and also Enceladus and Saturn. And if you click again, the slide shows an illustration of the sequence of events in TSSM with a launch planned around the mid-20s, similar to what is going to happen with Dragonfly, a 9-year travel followed by orbit insertion of the orbiter, which was going to be developed by NASA, and the release of two in-situ elements, a Montgolfier hot air balloon and a lake lander that were going to be developed by ESA. Yes, and the next slide shows the baseline of the mission architecture, where you see the in-situ elements, the hot air balloon that was going to float above the equator, and a probe lander in Kraken Marin, we thought we would put it in at the time. So the next couple of slides, I'll skip through. They're just showing the payload for TSSM. If we can go to the next one also, shows the payload for the in-situ elements and the Montgolfier. And you can find all of this information in the papers, like I said. And those were fantastic elements and in-situ precursors for what was going to happen next. And next is a slide that says that this mission, even if it didn't fly yet, I'd like to say, managed to hammer in one great point, which is that we need to continue exploring Titan from different points of view and with different new elements. And of course, the next one speaks to the fact that we now have the Dragonfly mission, which is the NASA New Frontiers 4 mission. And I'm sure you all know about it. So if we can click through the next slide, you have all the information. And this is a fantastic mission with a rotorcraft that will tell us a lot of things about the habitability in Titan's environment and explore locations on the ground, which we could not do with the rover. So my last slide is the one that says that we're in a fantastic era of exploration that will bring us from times of early discoveries to landings, going through all the missions that are planned currently. And with that, Tim, if you can click once more, I'd like to say thank you to everybody, to all the people who came together behind the Cassini-Huygens mission, and the organizers of IPPW in 2021, which was not an easy task, I'm sure, and you're doing an excellent meeting. Thank you very much.
Thank you, Elena. Very much. It's a great presentation. We have a question from Gilles. What is your most wanted finding from Dragonfly? And do you have any recommendations for the team working on that mission?
Yes, obviously, I think I talked to all the people on that fantastic mission. And like I said, I think it's wonderful that we'll be able to hop around on Titan's ground, which is the best thing we can do other than a balloon, which was our way of doing a rover without being, stuck on Titan's surface. What I really, really love is to make in situ measurements and analysis that would lead to a better understanding of the habitable conditions that we might have on Titan and the prebiotic chemistry, the chemical signatures that would be indicative of water-based or hydrocarbon-based elements that we could find on the surface. And I'm sure that's also foreseen along with the seismometer and the measurements we'll do with that.
And another question, what do you want to be the next mission after Dragonfly? A boat, submarine, a balloon, or a rover?
Oh, I do want a balloon. I do at some point. I didn't say it, but the Montgolfier brothers actually flew the first hot air balloon from Meudon. And there's many people in this meeting now, and I realize Pat Beecham is also there. Hi, Pat, and everybody else. We had such a fantastic time planning for this balloon because Titan's atmosphere is a great atmosphere. It's a great environment to fly a balloon in. It is really the best place. And the Montgolfier brothers are something of precursors in Meudon Observatory, and we flew the first hot air balloon there. And the next one I hope to see on Titan at some time.
Excellent. Thank you.
Thank you all very much again, and especially the Al-Sif Memorial Award Committee for thinking of me.
Okay. Next, we have a group of 4 speakers, and we're going to have questions at the end of the group, so please save them until that time. Our next presenter is Sam Albert. Sam is a graduate researcher and NASA Space Technology Research Fellow in the Autonomous Vehicle Systems Laboratory at the University of Colorado Boulder. His research focuses on mission design, uncertainty quantification, and guidance methods applied to aero capture. Sam received the Bachelor of Science in Aeronautical and Astronautical Engineering from Purdue University in 2018, and a Master of Science in Aerospace Engineering from CU Boulder in 2020. Sam.
All right, thanks very much. I just want to express how excited I am to be presenting here at IPPW, an event I've come to look forward to every year, and to, of course, acknowledge my co-authors, Dr. Bobby Braun and Dr. Hans-Peter Schatz. Presenting our work today, co-delivery of probe and orbiter via aero capture for interplanetary missions. Next slide. So we'll start out by covering our proposed co-delivery concept itself, and then at the end, if we have time, we'll go over a motivating example mission scenario. Next slide. So in the lower left, I'm just defining aero capture, which is the well-studied technique of flying through the upper atmosphere upon arrival to reduce a spacecraft's energy and capture into the desired orbit. This is beneficial because it can reduce the required propellant compared to propulsive orbit insertion. And I won't belabor the point because I think this community is pretty familiar with this concept. So look at the dashed box there, and it sort of zooms in this diagram I have in the upper right, which looks at our proposed co-delivery method. So in this, the probe and orbiter come in on the same approach trajectory, meaning they have nearly identical entry angle and velocity at the atmosphere interface. Then they diverge during atmospheric flight due to differences in their aerodynamic properties and their control approach. The motivation for doing something like this, for co-delivering a probe and orbiter, is that by targeting just a single entry state, the approach navigation can be simplified. So without this method, in general, you would require either propulsion on the probe or a divert maneuver performed by the orbiter. These options are certainly not impossible. We just heard a lot about Cassini and Huygens, for example, but they do present some challenges to design, and these challenges have become relevant in several past mission concepts. And this co-delivery method that we're presenting today provides one potential alternative approach. This is really meant for either ride-along secondary missions or for supporting infrastructure needed, like if you require a relay orbiter for your probe, for example. Next slide, please. So looking at this co-delivery concept, we started out by mapping feasibility of this co-delivery method across a broad trade space. Now this plot looks like a lot, but we'll go through it step by step. We're looking at Mars here, but we do also have results for Earth, Venus, Neptune, and of course Titan. So stepping through this chart now, we're looking at Mars, 6 km per second, planet relative entry velocity. The center chart shows ballistic trajectories. Go back to the previous chart, please. I'm saying, yeah, chart to mean the graph. Thank you. The center chart shows ballistic trajectories, and then the top and bottom show lift down and lift up trajectories, respectively. So if you look at the bottom where we have full lift up, the furthest left, the steepest entries, we're also varying entry flight path angle on the x-axis, and then on the y-axis, we're varying the ballistic coefficient, which I've defined in the upper right. That's just the ratio of your mass to your drag area. So looking at the bottom of this graph, the furthest left are the steepest trajectories, and that's our probe region. Those trajectories intersect the surface. Then on the other side, between those black and purple lines, we have our aero capture region, because these trajectories escape the atmosphere, they skip out, but at that point they are on elliptical trajectories, so these are valid trajectories for potential aero capture trajectories. And then further right still of that purple line, in that region, the shallowest entries also skip out of the atmosphere, but still have hyperbolic energy, and thus are not valid for aero capture or for probes. And so this is how we're going to capture feasibility of this concept. Now next slide, please. Thank you. So to look at feasibility, we'll look along vertical lines, because for this concept, by definition, we want different ballistic coefficients and or a difference in control authority to result in probe and orbiter trajectories occurring from the same entry flight path angle. So since entry flight path angle is on the y-axis, we'll look at on the x-axis, we'll look at a vertical line. And then we can put two other vertical lines, those dashed lines on either side of it, represent the entry corridor. So now we're beginning to capture some uncertainty in the problem. So if you want to be still feasible, accommodating for the uncertainty that results in this entry flight path angle corridor, you should be feasible along all three of these vertical lines, not just the center one. Next slide, please. So because we've also contoured other parameters here, including peak G load, peak heat flux, total heat load, and initial apoapsis altitude, we can enforce other constraints as well as mission designers using these results. So as an example, let's enforce that the orbiter requires an apoapsis of at least 300 kilometers altitude. Next slide. And just for an example, let's also enforce that the probe does not exceed a peak heat flux of 50 watts per centimeter squared. Next slide, please. So these constraints all lead to, given our assumption on entry flight path angle and our lift to drag ratio of 0.25, our lift up orbiter would require a ballistic coefficient of at least 130 kilograms per meter squared, and our ballistic probe would require a ballistic coefficient of no greater than 100 kilograms per meter squared. So you can see that corresponds to the regions shaded in gray, and this is meant to illustrate how you can enforce your own constraints on these charts, which, like I mentioned, are also available at other destinations. Today we're focusing on Mars. Next slide, please. So mapping this feasibility, we used bounding cases, and we just looked at full lift up or full lift down trajectories, as well as the ballistic trajectories. In general, though, if you're performing aero capture, you would like some closed loop guidance to guide yourself to your desired final state while mitigating any relevant uncertainties. So let's look at a specific example, a point design, so to speak, from that feasibility chart that meets the constraints that we just identified, and then let's implement closed-loop guidance and make sure that it performs as expected and that this point design is still feasible when we look at it in a little bit more detail. So we'll have an orbiter with a ballistic coefficient of 130, a probe with ballistic coefficient of 35. Those will both use bank angle modulation for their guidance. And we'll have a third vehicle that is a passive ballistic probe for the purposes of comparison. Next slide, please. So this chart has a lot of numbers, but the key takeaways are, number one, that the guidance performed as expected, as well documented elsewhere in the literature. It did successfully apply to this scenario, and we're able to guide the orbiter and the guided probe to their final states with reasonable error statistics. It's also notable on this slide that I'm pulling out here the statistics for the guided probe and passive probe with their range targeting error, and this is at 15 kilometers altitude, so sort of a stand-in for a parachute deploy phase. And you can note that the passive probe performs about 10 times worse than the guided probe in terms of range targeting. And of course, it's to be expected that guidance would improve your targeting results, but it's also worth noting that plus or minus 50 kilometers range targeting error, depending on your application, potentially that is sufficient. So it's also worth noting that if you want to simplify your design as much as possible and have a passive ballistic probe, not worry about guidance on the probe, depending on your application, maybe that is good enough. And so you can then directly compare guidance and no guidance for any particular scenario, which we've done just for one representative scenario here. Next slide, please. So like I mentioned, we'll now go through a specific example that would take advantage of this proposed co-delivery method. Next slide. So again, we'll use the point design that we just identified. This is an MSL-like orbiter, and it's a shield-like rough lander. So we'll use a passive ballistic example. Shield is a concept that's in development at JPL, and it's a rough lander that would use crushable material in place of any parachute or retropropulsion phases of EDL. And it really simplifies things as much as possible. And let's deliver more than one. Let's say we want 4 or more landers to form a network to conduct unique science on the Martian surface. And I will mention briefly that this is motivated by an ongoing Keck Institute study titled Revolutionizing Access to the Mars Surface. And Dr. Zach Putnam gave a great overview of this study at an earlier IPPW session that you can see in the archive. Next slide. I'll speed right through this. Essentially what we're doing is, I said earlier the probe and orbiter would have identical entry state. Really, it's nearly identical because they have to separate somewhat to first avoid recontact in the atmosphere, and second, spread out these multiple probes on the surface. And so you can vary the magnitude and timing of that separation maneuver to achieve different landed geometries on the surface. And we're showing that by separating in either the cross-track or long-track directions, you can achieve tens to hundreds of kilometers of separation on the surface by separating about a day out with 10 centimeters per second delta V. And then we vary that and see how that changes. Next slide.
2 minutes.
Okay, thanks. So this just shows the same data from that previous slide in perspective, where now we have axis equal, and we're showing it against a 2-scale image of the Martian surface. So to make a very apples to oranges comparison, if I may, Curiosity covered about 20 kilometers in its driving in its first 7 years of operation. Drawn this yellow line across a crater, and that is roughly double that distance at a little less than 45 kilometers, whereas the width of this image covers 1,000 kilometers. Now, obviously, each of these landers would be far less capable than a Curiosity rover, but the point I'm trying to communicate here is that for these fairly small delta Vs, shortly before entry, you can separate on the surface and you can conduct potentially simultaneous science far apart on the surface. Next slide. So to conclude, today I've discussed our proposed co-delivery method and motivated it, showed that it is feasible at Mars, and like I said, we have results for other destinations as well that are available in backup slides for the archive. Implemented existing guidance schemes and showed that those apply as expected, and noted that one appealing application of this co-delivery method is using an MSL-class orbiter and a shield-class rough lander. This may provide a path to a low-cost delivery of a network of small landers on the Martian surface. So to end, I'll just note I've got a picture from Marco here on the left, a GIF of Ingenuity on the right, and these are both 2 very exciting missions that were conducted by small ride-along craft at Mars. So let's think out of the box about the future of small spacecraft on Mars. Thank you, and I look forward to taking any questions.
All right. Thank you very much, Sam. We'll get to the questions at the end of the group of presentations. Our next presenter is Jan Adam. Jan received a master's degree in particle physics from RWTH Aachen University. Currently, he is responsible for the development of a sonar system as part of the four-field exploration system of a melting probe in the TRIPLE project line. This work is part of his PhD studies at Physics Institute 3B of RWTH Aachen. Go ahead, Jan.
Yeah, thank you for the introduction, and hello everybody. I hope you can hear me. Today I want to talk about FFRS, a four-field reconnaissance system for melting probes to explore icy worlds. And one of the most exciting icy worlds in our solar system is the Jubian moon Europa. Next slide, please. And Europa has a diameter of 3,122 kilometers. And as you can see in the artist view on the lower right, it's believed that below a thick icy crust, liquid ocean is located. And inside the ocean, there might be some, or possibly there's some hydrothermal activity. And this as a whole, from an astrobiological view, means a good environment for the development of life. And to get further insights on Europa, flyby missions are already scheduled by ESA and NASA. Next steps would be lander missions, and step further might be an exploration of the ice and the ocean in the future. And for these exploration missions, Triple is investigating basic technologies. Next slide, please. Triple is an acronym for Technologies for Rapid Ice Penetration and Subglacial Lake Exploration. In principle, three components are developed for scenario as shown on the right side. So a shuttle melting probe is melting through the thick ice crust and is transporting autonomous underwater vehicle into the ice. And there, this vehicle should explore the water and the region and take autonomously samples from interesting points. And these samples should be in situ analyzed in an astrobiological laboratory. And the whole Triple team consists of 12 German companies and universities managed by the German Space Agency SDLR. And just again, as I already stressed, the goals are to explore technologies for future exploration missions to ocean worlds in the solar system, and especially for the search of biosignatures in the ocean of icy moons. Demonstration of those components in a terrestrial analogous scenario is planned in Antarctica at Dome C region in 2025-26. I want to talk a little bit more in detail on the next slide about sub-project, the FRS, so the four-field reconnaissance system. And for the travel of the melting probe through the ice sheet, there are a crucial point is to find obstacles in the trajectory of the melting probe so that the probe can melt around them. And the second crucial point is to find the ice-water boundary to trigger an anchor mechanism so that the probe does not get lost in the water. Triple FRS is appointing this point with developing a four-field reconnaissance system built as a hybrid system of radar and sonar so that those complementary detection principles can be used. Radar is working very well in ice and airfilled crevasses. Sonar works well in fluids and might as well support the navigation of the AOV in the water reservoir. And a third component is the permittivity sensor, so that changing properties of the ice can be taken into account in the radar data evaluation. Next slide, please. We plan to integrate those systems into a demonstrator melting probe that has comparable installation space and interfaces to a candidate probe for the triple scenario. As you see in the sketch on the lower part of this slide, the permittivity sensor should be integrated more in the back of the probe, and radar and sonar system share space at the front. In the following slides, I want to discuss a little bit more in detail those subsystems. Next slide, please. Starting with the sonar. So we want to use the piezoelectric transducer as it is sketched on the right side. For this, or for the building of this transducer, there are several design challenges. So because we have to share the space in the melting head with the radar antennas, but still maximize the acoustic output of the transducer. And of course, because we want to put it into a melting probe, there's only limited size, and the melting properties of the melting probe should not be reduced too much. This design that you see on the right side is a preliminary one and will be further optimized in tests and simulations regarding frequency characteristics and beam characteristics. And to get really directional information to this melting head, as you can see in the sketch, as well, there are glued some receiver sensors to be able to do triangulation. Next slide, please. The design goal for the radar is to get a high range up to 200 meters with a high resolution below 2 meters. And again, here are the limitations that it has to be small size to fit into the probe, and that the melting process should not be disturbed too much. The proposed solution is to build a sequential sampling pulse radar with a central frequency of 1.35 gigahertz, as it's shown in the upper right. And this should be powered by a gallium nitride hemmed amplifier, as it is shown in the lower right. And by using a multi-channel approach, we want to do beamforming to get information about the direction of the received signals. And the radar antennas should be embedded into the melting head, and therefore they are made from aluminum nitride, because this has a very high thermal conductivity and can be very well miniaturized because of the high permittivity. Next slide, please. The permittivity sensor should be installed at the rear of the probe, and by detecting impedance variations in the near field of receiving and transmitting electrodes, as it is shown in the sketch on the right and in the picture of first prototype. We want to get from these impedance changes a suggestion of the difference in the permittivity. And if those measurements are compared to calibration measurements, the permittivity can be calculated. And for a robust result, it's required that the electrodes have always a good contact to the ice. Next slide, please.
2 minutes.
Thank you. There's an upcoming field test or planned field test nearly right after this session. So we will test our system on an alpine glacier in southern Tyrol, starting by tomorrow. And there we want to do first basic tests of the sonar and radar capabilities and try to detect in-ice targets in coincidence with the radar and sonar. As you see on the right in an aerial view of possible test sites. And these in-ice targets could be crevasses or maybe the bedrock of the glacier. And with the permittivity sensors, we want to do measurements of different varieties of changes in ice and snow. Next slide, please. And to conclude, in triple FRS, a 4-field reconnaissance system using a sonar and radar is developed, and we start with our first tests. And in the next step, we want to integrate a full FRS system consisting of the radar, sonar, and permittivity sensors in a melting probe that should be finally demonstrated in 2023. And triple FRS is part of the bigger triple project that explores technologies needed in future exploration missions to ocean worlds in the solar system. And for further information, please visit the triple-project website. Thank you very much.
Awesome. Thank you, Jan. Now I'm going to turn it over to Dimitri for introductions of the next upcoming speakers.
Okay, thank you, Robert. So I will take it from here. Our next presenter is Niraj Srinivas. So he will give a talk on full autonomous EDL for in situ measurement of exoplanets. Niraj is currently a PhD student at the Virginia Tech University with a research focus on autonomous navigation for entry, descent, and landing systems. And I think with that, Niraj, the floor is yours.
Thank you for the introduction, and I'm honored to present here at IPPW. I will be presenting our concept, which details an algorithm through which a fully autonomous entry, descent, and landing can be performed to make in situ measurements on exoplanets. Next slide, please. So what is the current state-of-the-art EDL? If you look at the Mars 2020 mission, we have used the terrain relative navigation technologies, which compares data that we have from orbiters around Mars, like the Mars Reconnaissance Orbiter. This data is then stored on board and compared to what the lander sees to identify the landmarks and obstacles, and then more or less autonomously make decisions that allow it to land at a safe target. This is a form of autonomous hazard avoidance, and it's mainly on the image data comparison. Next slide, please. Now, why focus on exoplanets? Why not planets in our own solar system? Exoplanets give us insights into the creation of the universe, and of course, it's a very curious thing to know about these systems. From so far as we've seen, the formation of other solar systems and star systems are different to what we have seen in our own solar system. So this would give us a valuable insight into how the universe works. And of course, there's the possibility of the finding of life on these planets. The problem with exoplanets, as we all know, is that they are far away. Just for an example, if you take the planet TRAPPIST-1d, it has been identified as quote-unquote super Earth, which is at around 39 light years away from Earth. So a mission timeline that consists of separate probes or separate satellites that go around the planet, mapping out the surface like what we do on Mars, and then sending a probe that touches down on the surface would take generations just to get there and come back and relay the data back. So through this concept, we are trying to cut down all those separate missions into just one mission that can perform in situ measurements of the exoplanet. In situ measurements give us much more insight as compared to remote sensing in the areas of tectonic activity, the search for life from the surface, the soil composition, etc. Because these planets are so far away, we cannot do a mission that relies on feedback from Earth to know what the next steps are. So the solution for this is complete autonomy. Next slide, please. So this concept of the algorithm that we propose is in the context of a mission timeline or a mission to an exoplanet. Now, the mission would first start with remote sensing. Remote sensing, of course, is being in orbit or during a hypersonic entry and looking at the features on the surface of the planet. Now, using instruments that we already use on probes on satellites like the Mars Reconnaissance Orbiter, such as the HiRISE camera, which has a resolution of 0.3 meters from 300 kilometers altitude, or the shallow subsurface radar, which can resolve up to 7 meter thin layers on the surface of Mars. If we use this in orbit of an exoplanet, we will be able to identify regions on the surface that are the most viable for landing. Now, as I said, we would not have any feedback from Earth, so the probe itself, the spacecraft itself, would have to determine where to land. Now, determining where to land is based on a lot of factors. Some of these factors include the reachability to that site, the surface roughness or the obstacles on that site, or the terrain roughness, you could say, and the potential for good scientific output. Now, by this, what I mean is landing on a riverbed or landing somewhere with a dried up lake would be much more beneficial to the scientific community for answering questions related to the formation of life or the amount of water in the soil, etc., as compared to landing on a rough mountainous terrain. Now, this ties into the overall mission context, as in selecting the landing site is the first step of complete autonomy. We have computer vision based algorithms that have can already detect features on the surface of the Earth. Implementing them on an exoplanet is the first step towards full autonomy. Next slide, please. Now, once the regions have been identified, how do we decide where to go and what to do? This comes down to enabling the system to have an intelligent decision-making process, and for this we have selected a Markov decision-based process. So the MDP consists of states, actions, policies, and rewards. Each action that the spacecraft takes from any one of its states will result in a reward based on where that action leads it to end up. Now, this MDP can be used to facilitate for autonomous guidance, navigation, and control. Incorporating a neural network to this reinforcement learning-based Markov decision process will give us a deep MDP, and this is basically what will allow us, or allow the spacecraft, to make completely autonomous decisions on its control schemes. Next slide, please. Now, how do we train this neural network to make the best choices? So, as you can see on the right, we have deployed, or we have simulated a Mars lander that is optimized to make the best control decisions possible from a specified entry interface to a specified end target location. So through an optimizer that controls the bank angle and modulates the bank angle, the spacecraft decides its own steps or its own control schemes to reach the selected target. And a model predictive controller has been implemented to overcome the wind disturbances that occur during this entry process. Now, for our exoplanet mission, we need to build up a bunch of these data sets of optimal control so that the neural net can be trained on those. Training the neural net on fringe cases and plenty of training data, that is training data with various entry interfaces, various wind models, various obstacles in its path, and various landing locations. Training that neural network based on this training data will allow us to create a robust model that can, in essence, predict the final landing ellipses through Monte Carlo analyses. So if you look at the picture, you can see a bunch of dots on the surface of Mars. These are some of the landing locations we got as the optimizer was run. And the trajectories that have been marked consist of the outside or the outlier cases. That is, how far away can we get from the final location, starting at this particular altitude.
2 minutes, Niraj.
Thank you. Next slide, please. What does this mean? This means that we can deploy adaptable control for the EDL system. This means that we can modify the trajectory in real time. If you look at the figure on the right side, the vehicle knows the green path is the best path to go. And because we have these trained neural networks on board, it knows that if it takes a particular step or a particular action at a particular time, it will end up in a different location, and that's detrimental. A risk versus reward based algorithm will be implemented that allows for this. Next slide, please. Design concerns. We do not have the atmospheric data for exoplanets, as we all know. So in a typical EDL mission, we need a good ballistic coefficient and a shallow flight path angle, but because the density is not known, it might lead to heating issues. So we may potentially require a mechanical system that can be adaptable. For example, a high ad-based system or a tensegrity actuator system like the tandem concept. Next slide, please. So if this algorithm is properly implemented, we will be able to implement a fully autonomous system which can make its own decisions in an alien planet or an exoplanet. This opens the door to a new class of missions, and it has also the potential to be deployed in the solar system on planets or moons that have been scarcely studied. Thank you for the time.
Yeah, Neeraj, thank you very much for your presentation. So our next speaker is Thomas Hancock. Thomas Hancock is the system engineer at Vorticity Ltd. His work focuses on novel EDL system design, aerodynamics, characterization, and trajectory modeling. He's currently leading several EDL-related research studies and supports the ExoMars 2022 parachute qualification program. So Thomas, the floor is yours, please.
Thank you very much for the introduction. Hello, everyone. I hope you can all hear me all right. It's appropriate to be talking about this just after the end of the last presentation. Those of you at the last IPPW session will have heard several presentations from some of our colleagues on the Ephesto project. We're not involved with the Ephesto project. The activity I'm talking about now is distinct, but the aim is similar. And the aim is ultimately to develop a flexible thermal protection system that can be used on inflatable heat shields, mainly for Mars entry. Next slide, please. So why do we need a flexible TPS? What's wrong with classical rigid TPS? Well, as I'm sure everyone in the community knows, there's a constant desire to land heavier payloads than ever before on Mars in particular. And there's a constant interest in landing those payloads higher than ever before on Mars. To date, much of the Martian service has been out of bounds, effectively. Anything marked orange or red in the surface elevation map, we've effectively been unable to reach because there isn't enough atmosphere to slow down. One of the key reasons we have this limitation is that our rigid heat shields are limited in size by the size of the fairing they're launched from Earth in. There's a solution to this that's been around, at least conceptually, for a good number of years now, and that's either to use deployable or inflatable aeroshells that increase their drag area prior to atmospheric entry. However, we can't use classical rigid TPS on such deployable or inflatable aeroshells. We need a TPS system that can pack with the deployable or inflatable inside the fairing and then unfold and deploy prior to atmospheric entry. Next slide, please. This particular study follows on from another couple of ESA-funded studies over the past 5 years. Those studies looked at what we can do with deployable and inflatables and what kind of missions they facilitate. As a result of those studies, we have a reference mission to Mars, some EDL system requirements, and a reference entry vehicle configuration. The roadmap on the right is the result of those earlier studies, and this follow-on activity covers the 3 boxes in green, which are all associated with TPS development. The aim of this activity is to increase the TRL in Europe of flexible TPS from 2 to 3. And in order to do that, we need to select materials, characterize them, design layups, figure out how to manufacture the raw materials into a coherent layup, and then prepare for future demonstration flights, either from high-altitude balloons or orbital re-entry, such as NASA's IRB-3 or LOFTID missions. Next slide, please. So the reference mission that we're designing the TPS for is to land approximately 1 ton at Mars Highlands, that's 2 kilometers above Mola. You can see a cross-section of the entry configuration on the right. That's a 60-degree sphere cone with a large rigid central section and a stacked toroid inflatable outer conical section. That stacked toroid inflates prior to entry, increasing the drag area. The entire windward surface of that reference vehicle is covered in a flexible TPS, and the role of that TPS is to keep the inner surface, i.e. the inflatable structure, no higher than 300 to 200 degrees Celsius, given the entry heat load. Next slide, please. So the baseline concept, this is a cross-section diagram of the flexible TPS, and this will look extremely familiar to a lot of people on the conference, because I know some of you have either read or worked on NASA's flexible TPS. and this draws very heavily on the excellent heritage that's been built up by NASA in this field. Consists of 3 functional layers. The outer layer, in red, is exposed to the flow, and its main job is to protect the underlying insulation layer material, which, if it was exposed directly to the entry flows, would effectively be stripped away, as these insulation materials tend to have relatively low strengths. The insulation layer forms the bulk of the material thickness of the layup, and for this you want a low thermal diffusivity material, which can delay the heat pulse associated with entry and keep the underlying structure within its temperature limits. Behind the insulation layer you have a gas barrier, which serves 2 purposes. Firstly, to prevent any hot gases or decomposition products from impinging on the inflatable structure underneath and potentially damaging it. And secondly, to provide a good structural backing to the insulation material, holding it in place. Next slide, please. So, where have we got to so far with the project? Well, for each of these 3 layers, we've selected a prime material and a backup material. And in collaboration with the Austrian Foundry Research Institute, ERGI, we've conducted fairly extensive material characterization testing on all of them. That covers thermal properties and mechanical properties. And the purpose of all of this testing is to really understand the materials and then use that data to perform thermal and mechanical design. Next slide, please. So I won't go through all the data, but I'll show you the materials we've selected and select a couple of key points. For the outer layer, the primary material of choice is Nextel 440, which is an alumina borosilicate ceramic fiber woven fabric. That's the pink fabric on the left there. Again, very familiar to anyone working on ERB-3 in NASA. That was what was used as the outer layer on that mission. It has several significant advantages. In particular, it's fairly strong at elevated temperatures. It's fairly manufacturable. It's been around a long time, and it's very well characterized. Another advantage is you have a sewing thread in the same kind of fiber. As a backup, an alternative, we have a silica cloth, which is on the right in green. As you can see in the microscope image, that has a much more significant fraying and small filament production. As soon as you handle that cloth, it starts to produce dust and fibers, which are irritants, and that makes manufacturing and handling a little more tricky than the Nextel. It's also very directional, the silica cloth. You can see in the tensile test results, it's much stronger in warp and has a higher Young's modulus in the warp direction than in the weft. A material we didn't select, but is really the gold standard when it comes to outer layers for flexible TPS, would be silicon carbide. That has the key advantages that it has a high emissivity, so you can re-radiate heat away from the layup, and also has the best strength at high temperature of any other material that's comparable. We didn't consider that for this project, mainly because it's extremely expensive and it takes a very long time to manufacture to order, whereas the other materials are nearly off-the-shelf available materials. Next slide, please. Underneath the outer layer, we have the insulation, and that's the bulk of the thickness. As I said earlier, we need a low thermal diffusivity here to slow down the heat transfer from the outer layer down through to the inner layer. The first choice is a graphite felt in black on the left. That's a European material produced in Germany. As it's carbon, it's only suitable for use in atmospheres where it's not going to significantly oxidize. However, if that's the case, it has a very high maximum temperature, well above 2000 degrees Celsius. It's a very homogeneous material and it's quite easy to manufacture. In contrast to that, you have backup material, which is a silica aerogel. This is a rather more heterogeneous. The composition varies and the properties vary across the material. Unlike the Sigrotherm, the pyrogel decomposes with increasing temperature. You can see some decomposition charts on the bottom there. It loses between 4 and 5% of its mass by the time you get to 1000 degrees Celsius, whereas the Sigrotherm, the graphite felt, is relatively unchanged. Next slide, please. And then finally, behind that, we have the gas barrier. 2 different types of material we're looking at here. One airbag material, silicon-coated Kevlar, which you can use construction techniques from airbags and stacked toroids. And then finally, Kapton, a polyamide film. That'll be very familiar from anyone working in multi-layer insulation. Out of the polyamide films and the airbag materials we looked at, those 2 had the best combination of good characterization data and good high temperature performance. Next slide, please. So that's where we've got to. We've selected materials, we've characterized them, we have all the data we need to conduct the design, and that's what we're going to get onto next. The thermal design will be performed by our partners Fluid Gravity, consisting of 1D thermal modeling and selecting the materials in the layout. We'll focus on the mechanical design and figuring out how we assemble these raw materials into a complete layout. And then when we have the layout designed, we'll proceed to test it under representative laboratory conditions. And the bulk of this testing will be very similar to the results that were presented by Burkhard at the previous IPPW session. You can see the DLR's L2K ArcJet facility in the bottom left-hand image, and that allows us to test with representative atmospheres and heat fluxes of Mars. Next slide, please. So in conclusion, we're advancing the capabilities within Europe for flexible TPS design and testing, and there's a big consortium that is gaining that experience. And if you show up at IPPW next year, I'll look forward to presenting the results of that design and how the TPS has performed in the laboratory characterization testing. Thank you for your time.
And them to the presenters. Maybe I will first start with a question for Neeraj. You presented you gave a presentation about actually using reinforcement learning for EDL task. How do you actually cope with the problem of adapting the system to the reality? Because we rarely have a chance to test such learning in realistic environment.
Yeah, so that's a really good question. One potential solution that we have thought of is simulating worlds or simulating different planets to make sure that this algorithm can cope with varying conditions of either the atmosphere or the wind modeling, for example, temperatures and terrain data. We of course have a lot of data about Mars and Venus. The atmospheric data, for example, we have a lot of it, and the terrain data to some extent. So we can validate the algorithm and the reinforcement learning based the algorithm on Mars and Venus, on the terrestrial planets, to say so.
Okay, I see. Thank you. There is also a question from Jill to Thomas. What advantage do you see with your flexible heat shield compared to a deployable one, especially regarding the diameters that you are considering?
There are, as you say, there are two categories of heat shield where you can extend the drag area, deployable or inflatable. I think one of the key advantages of inflatable is potentially increased stiffness and robustness. With the deployable, you typically have a sort of umbrella-like structure with spars folding out and the material stretched out between those spars. And the difficulty is retaining adequate stiffness in the material between the spars. Whereas with a toroidal structure, you essentially have pressure all the way around the toroid in the inflatable that can allow you to obtain increased stiffness and reduced deformation of the inflatable structure. However, they're two valid approaches. I think it's still worth investigating both of them and developing both technologies simultaneously.
Okay, thank you. The next question is from Elena Probst. Question to Samuel. What parameters do you consider the most important ones to define the entry interface point for area capture? For example, entry flight path, angle, entry velocity, etc.
Yeah, thanks, Elena. So in terms of the feasibility assessment, mostly the entry angle and entry velocity are important. When we're looking at, the energy that you have by the end of your path through the atmosphere and your peak heat rate and things like that. But in the case of looking at the map, we begin with an assumption that all of the 6 state components at entry are identical, back propagate to the time of the maneuver, apply that maneuver, and then forward propagate again to see the full effect of that maneuver. So it's capturing the differences in where the entry occurs on the atmosphere in addition to the entry angle and velocity. Thanks.
There was another question to you, Sam. What type of guidance algorithm was used for the BAM?
Yeah, so I'm chatting with Jens a little bit in the chat here, but basically we use a numerical predictor corrector approach that's been pretty well studied in the literature, the fully numerical predictor corrector entry guidance, or FNPEG, and the equivalent guidance for error capture FNPAG. We chose that because it's pretty well studied, and we wanted to use something with a lot of work in the current literature for our purposes of demonstrating feasibility using this existing guidance approach. Thanks.
Okay, great. Thanks a lot. There is also one question to Neeraj. Could you please elaborate a bit more on the data return capabilities? Like, how do you plan to get the data back from the probes? Radio, optical link, or what options did you consider?
Yeah, so two major problems with getting data back is the enormous power required to transmit something from light years away to Earth, and the potential of noisy data receiving back at Earth. So one thing that we have thought of that can potentially help this is to deploy little spacecraft at stable points along the trajectory to the exoplanet. These can be at stable points such as Lagrange points on the trajectory, which can act as repeaters or amplifiers to strengthen the signal back, whether it's optical or radio. So we can avoid the noise and reduce the power level required for data transmission. I hope that answered the question.
Okay. There's another question for Thomas. How does the flexible TPS system maintain stiffness and shape in something like a morphine HIAD?
Okay, so the reference vehicle we are considering in this particular project isn't a deliberately morphing inflatable decelerator, i.e. we're not designing it so that you can gain some kind of lift over drag advantage by the deformation. That's not to say that it won't deform, it will absolutely deform under the aerothermal loading, and indeed under any kind of tension that you pre-impose on the structure. In terms of adapting a flexible TPS to morphing IADs, I haven't worked on morphing IADs. I think that question would best be answered by someone who has directly. And I know there's a good deal of experience at NASA available in this, and indeed some of the hosts of this session have worked on it. So I'll have to pass on that question, I'm afraid.
Okay, I see. Good. Thank you. There is another question for you. Have there been any consideration as to the pressurization process? Maybe at how it would be done, pressurized storage tank used versus chemical reaction to inflate the TPC, etc.
So in the previous ESA studies, we did a trade-off of the various inflation mechanisms that are currently available, with a particular focus on ones that could be sourced in Europe, because the ultimate aim of this is to develop a European capability to build and manufacture these decelerators. So there are a number of different options, as you suggest. I think we were looking at cold gas generators mainly. It was the preferred option. But I'll have a look and get back to you via the chat on that.
Okay. Do you know when let's say TRL level 6 will be reached?
It depends how quickly we move on to an orbital reentry. That's the ultimate objective. And I know Efesto, their roadmap is very much towards an orbital reentry as quickly as possible. NASA have already done that with OV3, and they're planning to do that again with Lofted. That's where we need to get to in Europe.
Okay, great. So I don't see any more questions in the chat. All right, then if there are no more questions, then I would say we'll make a short break and come back to the second part of our session at 9:35 US Pacific time or 6:35 p.m. European time. So we'll have a 10-minute break and reconvene here just in 10 minutes. See you all there. So, welcome back, everyone. I think we can start with our next presenter, and that would be Benjamin Hochman. So, Benjamin Hochman is a robotic technologist at JPL, where he developed advanced robotic locomotion and autonomy capabilities for future exploration missions. Ben has worked on rovers that roll, climb, drill, rappel, and hope to overcome extreme planetary terrains that challenge traditional mobility systems. This project was inspired by Ben's PhD work on hoping tumbling rovers for the microgravity environment of small solar system bodies. So it's a very interesting work. Dr. Hochman, welcome. The floor is yours. Please keep in mind you have 10 minutes.
Thank you. Can I get a quick audio confirmation? You can hear me?
Yes, we can hear you.
Okay. Well, hi, everyone. This is going to be a talk on an interesting concept I led this past year, basically studying how we might observe the gravity field of small bodies more accurately. And this is a project in collaboration with University of Colorado Boulder, Dan Shears and Jay McMahon, as well as a student collaborator there, Jacopo Villa. Next slide, please. So just to orient everyone, what I mean when I say small bodies, it's a very broad category of objects in the solar system, by far the most numerous of the objects. And it encompasses things like near-Earth asteroids, comets, long-period comets, short-period comets, as well as some moons of bodies like Mars that are too small to become spherical. And in this talk, it'll be mostly focusing on any of these bodies that are less than tens of kilometers, so perhaps not including bodies like Ceres. So we're talking about the smallest of the bodies in the solar system. Next slide, please. The problem with previous missions, we've seen a lot of missions to these small bodies recently, but we still know relatively little about the interiors of these bodies. That's because these three methods that we traditionally use for probing planetary interiors face a lot of challenges for small bodies. And I apologize, I have some animations buried in here, so can you just click next? And one more. And so the focus of this talk will be on adapting gravity science techniques, which traditionally take the form of tracking or orbiting satellites with extreme precision to infer the mass distribution of small bodies. But that faces a lot of challenges on small bodies. Next slide. And just click, yeah, one more. Just to show you that we've learned a lot using gravity science techniques at bodies other than even the Earth. The Moon, we've done extremely well with the Braille mission. And this chart is kind of a snapshot to show you how accurately we've been able to map the gravity field of various bodies in the solar system. And the bottom line is gravity fields are easier to observe for larger bodies, missions that have more precise orbit determination, orbits that we're able to get at lower altitude, and longer integration. All of these are challenges when we go to small, irregularly shaped bodies that don't allow for low altitude orbits. The next slide, please. So up until recently, this observation by OSIRIS-REx, we haven't been able to observe the gravity field with extreme precision at any of these small bodies, but serendipitously, OSIRIS-REx actually discovered a collection of naturally ejected particles that are essentially centimeter-sized rocks that were being lofted off of the equatorial region of Bennu, and they were actually able to use multiple images of this particle swarm and track some of these particles to infer the gravity field of Bennu far more accurately than they could do with orbit determination methods alone. So this observation, while it faced a number of challenges and these particles were very difficult to observe, it inspired this concept that I'll talk about today. Next slide. And what we're calling that is gravity poppers. This is originally a NIAC study, and the concept is fairly simple. A spacecraft arrives in proximity to a small body. It deploys a number of very small minimalistic probes to the surface. These probes, once impacting the surface, they'll come to rest and then hop in some random trajectories, and that process is repeated. And then the idea is by observing the trajectories of these artificial probes from a remote observing spacecraft, we can then infer the gravity field very accurately given their low altitude. Next slide. Okay, this is a video. Hopefully it plays. Okay, yeah. Apologies for the frame rate, but this is just to show a animation of what this might look like from the spacecraft perspective. So essentially what you're seeing here is a swarm of, in this case, just spherical objects that are deployed to the surface of, in this case, Comet 67P CG. And this is really to illustrate the amount of data that the spacecraft is continuing to collect as it observes the hopping trajectories of all these probes. And the idea is, although this looks very chaotic, we can actually reason about these trajectories to infer very detailed mass distributions of the underlying body. Next slide. Okay, and just click through these three. So yeah, that's all. So this study had kind of three main focus areas to understand the feasibility of this concept. One being the tracking system. How do we actually track these trajectories of this swarm of probes, and what kind of precision can we get? The gravity estimation itself, which is really the core of the study, and that is to assess what the observability is of the gravity field given this type of measurement modality. And then finally, the probe design. What might the probes need to look like, and how might they behave in order to realize this mission? Next slide. And yeah, 1, 2, 3. Okay. For the tracking system, we considered three primary modalities for tracking the probes. One being an angles-only approach, which you could achieve with a camera, onboard camera from a remote observing spacecraft. That the idea is the probes would be bright enough to be visible in images, and that would provide relative angle measurements with respect to the spacecraft. The second modality complements that in the sense that it gives you a ranging and or Doppler range rate constraints between the probes and the mother spacecraft. And the third would be to do ranging through onboard radio communication between all the probes that can see each other. That has the potential to dramatically increase the number of measurements, although as I'll show later, the probes are a little bit too simple, and we don't expect that this might be more difficult and require future work. The radios would have to be a little more sophisticated to enable that. So in this study, we focused on imaging, basically because we implemented that in a simulation environment and saw that it worked quite well. So next slide. And just click. Yeah. And one more. So this slide summarizes our results from the optical tracking study, which we found to be the most promising mode for tracking the probes. Essentially, we could establish requirements on how bright the probes need to be in order to be detected by a distance camera, both in front of the small body, where the body's reflected light itself acts as a corrupting signal, as well as in front of the dark sky around the body, where the probes are much more bright. And the bottom line is with the proper brightness, we can centroid the probes between about 0.01 and 0.1 pixels, allowing for fairly precise angular measurements. Another key feature that enables this high resolution gravity estimation is the temporal frequency with which we can take these images. And so in order to reduce the data downlink requirement, autonomous image processing to identify and detect the locations of all the probes in an image is a critical enabling technology. And in order for the probes to be bright enough to be detected by a distant spacecraft camera, we considered two approaches. One in which the probes are just diffuse white spheres that reflect sunlight passively, and the other is an active strobing probe in which the probes themselves can be much smaller, but they rely on onboard LEDs and the synchronized strobe to be visible. For many reasons, we found that the LED strobing concept was preferable, and I'll detail what the probe with that modality looks like later.
2 minutes.
Next slide. Okay. So the gravity estimation work was the core of the study, and basically we wanted to, in a high-fidelity simulation environment, validate that the gravity field can be observed to the resolution we think it can be. Next slide. Just click through here. These are all the assumptions we put into the model. Basically, the bottom line is we had a series of conservative assumptions, and we simulated 5 probes hopping for 16 hours. Next slide. And one more quick. So this is the money shot here. This shows that the gravity field can be observed far more accurately than what we could get with OSIRIS-REx, and even the particle tracking on OSIRIS-REx beyond degree in order 40. we were limited computationally to degree in order 40, so perhaps we can even observe gravity harmonics beyond degree 100. And on the left there, that's an image of what the spatial frequency of such a gravity field would look like. So this would allow us to start to answer interesting questions about the mass distribution and even weigh surface features like boulders. Next slide. We did a few sensitivity studies to measurement frequency. Next slide. And to measurement error, finding that better centroiding and more frequent measurements help. Next slide. And one more. So this is what the probe design looks like. On the outside, it's about 5 centimeters on an edge. It's a little cube, and this is a very notional design. It has an omnidirectional array of LEDs and deployed landing legs. Internally, it has a power system for strobing those LEDs, as well as an inertial reaction wheel for hopping randomly. Next slide. And this is what the concept would look like integrated into an instrument that might be hosted on the spacecraft, where we have a cache of a few dozen probes and a camera for tracking them. Next slide. So in conclusion, just pull all these bullets up here if you wouldn't mind. So we demonstrated that the gravity observability of such a concept could be beyond degree 40, which is order of magnitude better than the state of the art for these bodies. We identified key parameter sensitivities that need to be further explored. We identified that optical tracking with a remote camera seems to be sufficient for high fidelity gravimetry. We developed a notional baseline probe concept that's only 200 grams, so the spacecraft could in principle accommodate many of them. And the whole system we conceived of as a very small, less than 10 kilogram hosted instrument. So all that being said, lots of future work remains, including higher fidelity simulations and broader exploration of the trade space. I think I do have one more slide, apologies. And just click through the end here. So we think this technique can apply to bodies that are between 100 meters and 10 kilometers. That seems to be about the sweet spot. It could be used to estimate the interior morphology, mass distribution of asteroids, comets, and small moons. We also demonstrated that we can weigh this observable surface features, such as large boulders, and we can perhaps even identify and localize the presence of subsurface anomalies and voids, which would be interesting for resource prospecting. Another interesting component might be looked at in the future is time-varying gravity fields, for example, tidal variations or perturbations of Apophis during its flyby later this decade. So I apologize, I might have went over, but that's all I have.
Well, thank you, Benjamin, for the presentation. And I'm introducing now our next speaker, Dimitri. Dimitri received his PhD in electrical engineering from the Graz University of Technology in Austria in 2006. He was a teaching assistant from 2001 to 2006 and an assistant professor from 2006 to 2009 with the Signal Processing and Speech Communication Laboratory at Graz University of Technology. He joined the Department of Electrical Engineering at Princeton University in 2009, where he worked as a research associate until 2011. And in 2011, he joined the Institute of Communications and Navigations of the German Aerospace Center, DLR, where he is currently the head of the Swarm Exploration Group. Well, take it away, Dimitri.
Yes, thank you very much, Elena, for introduction. So I will be talking today about the concept that we develop jointly with colleagues from Planetary Science Institutes, and it is dedicated to active seismic exploration and subsurface imaging using adaptive intelligent sensor networks. So if you think about the concept, next slide, please. Apologize for animations. The slides have some animations in it. So the idea essentially is to use a robotic platform that can deploy multiple active sources that are placed in essentially sensor boxes, and these sensor boxes can be used as a source signal, but also can be used as receivers of acoustic signals. And essentially the idea, can you please click on a slide? Yes, and maybe the video should start me now. So the idea is that the robot will be able to position these boxes at different locations in order to make measurements. And what we plan to do is to equip these boxes with also computing capabilities so that the system is able to analyze the underlying structure and make suggestions how to change the deployment configuration to better highlight certain features that might be interesting. So the possible use of the system we see primarily near surface exploration of underground cavities, lava tubes, on the moon or Mars, just characterization of local geological subsurface structure, search for water ice, and the system should be primarily used as an addition to other subsurface exploration instruments like ground penetrating radar or measurements from the orbit. Next slide, please. As an active source, of course, it would be nice to have something like a huge explosion, which is probably impractical in real situations. So we are thinking about two types of solutions to generate an acoustic source. So one is a low velocity penetrator, similar to that used, for example, for InSight mission. An advantage of the system is that it can also go inside and produce the excitation from within the subsurface, if it is, of course, successful. Another approach would be to use an specially adapted accelerated wave drop system that can be used as an excitation source. So it's currently used already for exploration task on Earth. So it's just a matter of adaptation of this technology for space application. And we are targeting somewhere the range of maybe 2 kilograms of mass that would allow us to explore the local subsurface features. Next slide, please. Of course, in order to make the system operational, we need to ensure that there is a possibility to exchange information between these nodes, between the sensor boxes, and also we need to provide a common time base and coordinates. So we need to make sure that the data we acquire, first of all, recorded synchronously, and second, we know the exact position where the sensors are. For this purpose, we have already worked quite some time on developing a specialized, customized communication, navigation, and timing system that essentially uses a similar structure like a Wi-Fi, but adapted for swarm application. So the system allows in real time data exchange and communication between the nodes. So what you see right now in the video, maybe you can click 3 times. You should be able to see. Tim, can you click? Yes. So what you see here is is a test of the system that we performed 2 years ago. There are 3 local anchors that allow, in general, the system to compute 2 coordinates, to navigate or to localize in 2D, as well as compute the common time bases. However, there are certain areas that are that block access to one of those anchor points, and in general, this system would not allow to navigate. But this swarm concept that we promote and that we develop will allow the system to operate automatically, and even in cases when there is no direct line of sight, we will be able to localize every either moving or stationary object, as well as provide a common time base. Next slide, please. Another aspect that we are working on right now is the development of algorithms that would allow the analysis of the data. The focus here lies primarily on development of distributed imaging techniques, so that we know from seismologies. One of the basic one is, for example, sparse blind deconvolution, where the idea is to essentially estimate the excitation signal that is produced by an acoustic source and a reflectivity signal which actually characterizes the underground structure below the sensors. So we developed already algorithms that permit this decentralized processing of this data without requirement of sending the data to the Earth or sending it to centralized processors where the data analysis take place. Next slide, please. And this, in turn, this distributed approach data processing allows to then identify the layers of velocity in different layers, as well as the depth of the structure. And this can be again done without transmitting the data to a central location. Next slide, please. Another technique that we are developing is a high precision, high resolution technique known as a full waveform inversion. So the idea here is to deploy physics-based description of a wave propagation and try to essentially reconstruct. Can you click, please, several times? Click one more time, Tim. Yes, further. One more time. Yes, that's okay. So the idea here is essentially try to match the measurement performed by the sensors with a model of the wave propagation through the material. And this matching can be then formulated as an optimization problem where the goal is to identify the wave velocity, or essentially the value of the velocity in every point in the underground structure. And this problem can be solved also in a distributed fashion, such that all sensors at the end are equipped with information about the wave velocity distribution over the volume, and then can cooperatively make decision how to adapt their topology in response to that. Next slide. We did several simulations to compare the performance. Again, this is a synthetic case where we construct like an artificial object at depth of approximately 500 meters, and starting with initial model that unfortunately has to be relatively close to the true model, we are able to show that distributed approaches perform actually just as well as centralized approaches, and reconstruct the structure of the interior. Next slide, please. So to conclude, we think that active seismic can be used as a very efficient tool for local subsurface characterization. Such approach can augment existing remote sensing, magnetic and ground penetration, radar measurements. We also think that adapting the seismic technology to make the system more autonomous and to adapt it to the particularities of the terrain is a really important tool. There is also a possibility to process the data in a cooperative fashion without actually sending it back to Earth, or not necessarily sending it back to Earth. The first step, we are thinking about developing such sensor boxes, which will be based on a mascot model developed at the Robotic Institute at DLR. We will further work on techniques for full waveform inversion. And we're also thinking about doing first field studies to better acquire ourselves with the data and characterize or at least get a little bit more familiar with real data in those environments. Okay, thank you very much.
Thank you, Dimitri. Our next speaker is Atul. Atul is a PhD candidate in the School of Aeronautics and Astronautics at Purdue University. His dissertation work focuses on the development of a systems framework and analysis tool for rapid conceptual design of air capture missions. Take it away.
Can you hear me?
Yeah, we can hear you.
Oh, thank you. So, hello everyone, my name is Atul. I'm from Purdue University, and today I'm going to talk about a concept which would allow us to have large constellations of small satellites for planetary science at Mars and Venus. Let's go to the next slide, please. So, over the last 10 years or so, we have seen how small satellites are able to do big things in low Earth orbit. For example, Planet Labs have these constellation of doves, which are small 5-kilogram satellites, which have the capability to image the entire Earth every day. Similar applications are possible with synthetic aperture radar, wherein small satellites weighing less than 100 kilograms are able to view the Earth in radar and even view with repeat passes of radar every day, of the Earth every day. Now, what makes these kinds of applications possible? One is that the instruments are now miniaturized. What used to take a big spacecraft weighing thousands of kilograms can now be done with small spacecraft. The other thing is over the last 10 years, we have been able to send these kinds of small satellites into space economically, and this enables large constellations to be placed with low cost, much lower cost compared to large satellites. The question we ask in this talk is, can we extend this kind of capability using small satellite constellations to planetary exploration? And we have seen some parts of this come alive with the Marco spacecraft, which are small spacecraft which were sent to Mars. And these were 14 kilograms for comparison. Let's go to the next slide, please. Now, we have to understand that getting into orbit for small satellites is a very difficult task. For example, for comparison, the Marcos only had a delta V capability less than 50 meters per second, whereas if we decide to insert these satellites into Mars orbit, let's say a 400-kilometer circular orbit, the requirement is 2,500 meters per second. So there's a large gap in the available propulsive technologies for small spacecraft. To enable these small spacecraft to get into circular orbits around Mars and Venus, aerocapture is recommended. Aerocapture will enable access to orbit for small spacecraft. Here's an example concept shown for a small spacecraft with an adept drag modulation aerocapture system. The system is stored inside an EFTA volume for launch. It will deploy to like an umbrella just before entry. It will perform aerocapture and will insert the spacecraft into orbit. Drag modulation essentially gives the spacecraft, eliminates the limiting constraints for delta V from a propulsive standpoint. That is, we are capable of going into any orbit we want with drag modulation aerocapture. And drag modulation is particularly attractive because we can pack these spacecraft, pack small spacecraft, even large numbers of them, into small volumes, and we can send large numbers of them in a single mission. So drag modulation is a technology which enables access to orbit, which is very helpful for small satellites. Let's go to the next slide, please. Now, the other question is, how do we enable constellations? And this is done using what's called B-plane targeting maneuvers. This has been done many times in the past, wherein we have delivered, for example, orbiters and probes, for example, the Pioneer Venus missions, which had multiple probes. The idea is that the spacecraft would pack a number of these small spacecraft inside, and then it would perform trajectory correction maneuvers on its way to Mars or Venus and target different points on the B-plane. On the figure shown on the right is an example of B-plane targeting. We have shown here an example of 9 separate points on the B-plane. And the interesting thing about a circle in the B-plane is that all of them have the same entry flight path angle. So they all will have the same entry conditions for aerocapture. And what would be different is that they would all go into different inclination orbits. So a cruise stage which performs targeting maneuvers will aim a number of small sat at different points on the B-plane. And preliminary analysis shows that the amount of delta V required to do this kind of B-plane targeting maneuver is only a few meters per second. And so with a few meters per second of delta V, we can deliver these small satellites into different points on the B-plane, which would then translate into different inclination orbits. Let's go to the next slide, please. So this is a mission concept for establishing planetary constellations with a single launch. Just like we have large constellations on Earth, we can have tens or hundreds of small satellites in orbit around Mars. There's great flexibility in orbit selection. The aerocapture maneuver itself allows both low circular orbits and elliptical orbits, so there's flexibility in that dimension. And the B-plane targeting, basically the fact that you can target any point on the B-plane means that we can target near equatorial to very high inclination orbits. And one can one can envision something like this is an example I took from the ADEC project team for the SR1 flight test. In the near term, one could even envision that we could have a few of these riding along with a larger mission and being delivered to Mars or Venus along with a larger mission. Shown on the right here is a figure which corresponds to the kind of inclinations you get for the different B-plane targeting points I showed on the last slide. So with this approach, we are able to insert constellation of satellites, large numbers of them, into any kind of orbit you want, and this essentially opens up a new class of missions for planetary scientists to think about. Let's go to the next slide, please. So we looked at a couple of examples of applications for this kind of technology at Mars and Venus. Shown here on the left is a high inclination global imaging constellation inspired by the Planet Labs constellation in low Earth orbit. This constellation has about a few hundred satellites, all of them which can be delivered in a single mission if you have a sufficiently large crew stage. And this would allow us the capability to basically image Mars, the entire Mars every day, just like Planet Labs does on Earth. And we have thought of similar application for Venus. It's a high inclination synthetic aperture radar. Radar is better suited for remote sensing observations at Venus because of the cloud layer. And we could have about 10 satellites, each weighing 100 kilograms each, carrying a radar instrument. And this would allow us to basically image Venus in radar with much higher resolution than was possible. And the advantage of this architecture is that we think this can be done with much lower cost than a single large spacecraft weighing a few thousand kilograms. And let's go to the next slide, please. So I want to summarize. The takeaway point from this presentation is that a drag modulation error capture with ADEC will enable small satellite constellation Mars and Venus to be viable within this decade, enabling us to do the kind of things that we can do today in LEO and collect large amounts of data at a fraction of the cost of one large mission, one large spacecraft. I also want to take a moment to tell everyone that I finished my PhD. I successfully defended my PhD thesis. I was working on error capture. And I had the opportunity to give a talk at IPPW during every year of my PhD. And I really feel fortunate to be a part of it and be able to do this. So I want to thank the entire community for having me and giving me this opportunity. Thank you.
Well, thank you, Atul, for your presentation, and congratulations for your defended PhD thesis. Our next speaker is Hillary. Hillary is a scientist with the Terrestrial and Planetary Environments team in the Natural Environments branch of the Engineering Directorate at NASA's Marshall Space Flight Center. As Planetary Global Reference Atmospheric Model, short GRAM lead, she has utilized the developed planetary grams for diverse mission applications, including Mars Reconnaissance Orbiter, Mars Science Laboratory, Cassini, Mars Ascent Vehicle, and others. Hillary is the atmosphere modeling lead for the GRAM upgrade task. The floor is yours.
Hi. Sorry. I seem to be having an issue with my camera. I'm not sure why. Just 1 second. It's not. I'm getting audio, but no camera. Well, I'll go ahead, I guess. It was working earlier. Now it's saying it needs to allow camera and microphone. That's very odd. Because the preferences show, anyway, I will just continue forward without the camera. Thank you for the introduction, and I'm very happy to be presenting at IPPW this year. Hopefully next year we'll be in person, but hi to everybody virtually from Huntsville, Alabama. Next slide, please. Today I'm going to be talking about the GRAM upgrade task and the latest advancements and achievements that we've made. The GRAM upgrade team is made up of members from Langley Research Center and Marshall Space Flight Center, and our roles and responsibilities are listed on this slide. Next slide, please. The GRAMs are an engineering-oriented atmospheric model that estimate mean values and statistical variations of atmospheric properties for numerous planetary destinations. They are currently available for Earth, Mars, Venus, Titan, Neptune, and Uranus. The outputs include atmospheric density, temperature, pressure, chemical composition. For Mars GRAM, they include radiative fluxes and wind components along a user-defined path. The GRAMs do include seasonal, geographic, and altitude variations, and they're widely used by the engineering community because of their ability to create realistic atmospheric dispersions, and they can be integrated into high-fidelity flight dynamic simulations of launch, EDL, aerobraking, and aero capture. Next slide, please. We also include an optional trajectory input file consisting of time, height, latitude, and longitude that the user can use to provide the GRAM trajectory path. And we have an optional auxiliary profile consisting of height, latitude, longitude, temperature, pressure, density, eastward wind, and northward wind that may be used to replace the existing model data in the GRAMs. It's important to remember that the GRAMs are not a forecast model, and the GRAMs are available through the NASA software catalog at software.nasa.gov. Next slide, please. Since fiscal year 2018, the NASA Science Mission Directorate has provided funding support to upgrade the GRAMs. The primary objectives of the upgrade task are to modernize the code. This includes developing a new framework that transitions the original Fortran code to C++, while taking advantage of the object-oriented capabilities of C++. The second objective is to upgrade the atmosphere models within the existing GRAMs and establish a foundation for developing GRAMs for additional destinations, including Saturn, Uranus, and Jupiter. The third objective is to socialize plans and status to improve communication between users, modelers, and developers. Next slide, please. The first step in code modernization was to establish the GRAM suite. The GRAM suite is a common C++ framework that simplifies the model updates, integration, testing, and maintenance. It is a common framework that supports all solar system destination models and provides a uniform user interface for all of the planetary GRAMs. It includes a C++ library with C and Fortran interfaces, which can be incorporated into a trajectory or orbit propagation code. The first C++ releases of the re-architected legacy planetary GRAMs are straight conversions from the latest Fortran version. New model updates are being developed as part of future GRAM upgrades to the legacy planetary GRAMs. Next slide, please. We have made upgrades to the model within the GRAM suite format. The first upgrade is the GRAM ephemeris has been upgraded to the NAIF SPICE toolkit. We are working with the Veritas and DaVinci Plus teams to determine potential mission support by the GRAM team and utilization of the collected atmospheric data in Venus GRAM. We're also going to be in the next phase of the GRAM upgrades within the atmospheric models, upgrading the Titan GRAM atmosphere models. The GRAM team has also distributed funding since fiscal year 2020 for the following projects to improve the atmospheric data in the GRAMs. We have provided support to Sanjay Lamay and Patrick Fry at the University of Wisconsin, and they're reanalyzing the Venus Express radio occultation observations, as well as analyzing the Akatsuki data, thermal imaging data. And we look to use those in future GRAM upgrades within the GRAM suite. We've also provided funding to Hampton University, Cuneo, Justin, and Ryan at Hampton University, and they're developing global models for Venus, Jupiter, Saturn, Uranus, Neptune, and Titan. Next slide, please. Within the GRAM suite, we have also improved the speed of sound calculations. Within the GRAM suite, the GRAMs compute speed of sound based on a thermodynamic parameterization using density, pressure, and gamma, which is the ratio of specific heats, for a given constituent gas mixture. The GRAM legacy codes used a constant gamma, which was physically unrealistic. Analyses that we have done have shown that this formulation overestimates the speed of sound by as much as 10%. The GRAM suite uses an improved methodology for computing gamma, which involves the evaluation of Shoemake coefficients in runtime for the current constituent combination. Currently, we're working on future development that will replace the showmate coefficients with a high precision specific heat values derived from detailed quantum mechanical computations. Those computations have been completed, and it's anticipated that we're going to include these computational values in tables in an upcoming release of the Graham suite. Next slide, please. We also, in terms of new Mars model data, we have received updated MGCM data sets from NASA Ames Research Center, and they included low, average, and high depth cases for 12 LCBS values in 30-degree increments from 0 to 360. This data also includes new explicit longitudinal and time of sol variability. The legacy MarsGram MGCM data was based on diurnal and semi-diurnal tidal components, and our team is currently determining the best method of implementing longitudinal and time of sol variability that's included in this new MGCM data set into MarsGram. We're also coordinating with Steve Booker at the University of Michigan to obtain MGITM data that will replace the MTGCM data that's currently in the legacy version of MarsGram. MGITM, which includes the MAVEN mission data, and updated MGCM data will be incorporated into a future Graham Suite release. Next slide, please. This is a list of our upgraded Graham releases. First, we released Graham Suite version 1.0 in May 2020, and that includes the re-architected Neptune Graham, which includes the common Graham framework and the planet-specific code. We also have Makefile and Visual Studio solutions for building the Graham Suite included in the distribution file sent to the approved users. A Neptune Graham user guide, a Graham Programmer's Manual, which is a new tool that we're providing users, which is a comprehensive, very detailed manual that contains all of the C++ programming intricacies. So if you're interested in the guts of the Grahams, we now provide a detailed C++ programmer's manual. We also include examples and tests for successful implementation of Neptune Graham. We followed up that release with Graham Suite version 1.1, which was released in September of 2020. That added the re-architected Titan Graham, again with the common Graham framework and the planet-specific code, a Titan Graham user guide, and examples and tests for successful implementation of Titan Graham. The re-architected Mars, Venus, and Earth Grahams will be released in future versions of the Graham Suite. Next slide, please.
2 minutes.
The really exciting news that I want to present to the IPPW community is that we have a new Graham added to the Graham family, and it's Uranus Graham. And it was released in Graham Suite version 1.2 in this month, and it includes the common Graham framework and the planet-specific code as before. The Uranus Graham atmospheric data is from the NASA Ames Research Center Uranus atmospheric model developed by Gary Allen, which is based on Voyager radio science, infrared interferometer spectrometer and radiometer, the IRIS, and UVS data from the Voyager 2 flyby of Uranus. The model includes atmospheric density, pressure, temperature, and chemical composition for helium, hydrogen, and methane. It does not include wind data. We have included a Uranus Graham user guide in the release and examples and tests for successful implementation of Uranus Graham. Next slide, please. Other upcoming new Graham releases, new Grahams to the Graham family, are Jupiter Graham, which is based on Galileo probe ASI data from Steve et al., which includes atmospheric density, pressure, and temperature. It does not include chemical compositions or winds. This will be released in a future version of the Graham Suite, probably in the next couple of months. We also have Saturn Graham, which is currently under development, and will be released in a future version of the Graham Suite. Next slide, please. In summary, the Grahams are a vital and frequently used toolset that influences mission selection and decisions. As I mentioned, the upgrades of the existing Grahams and development of new Grahams are ongoing. Graham Suite version 1.2 has been released and is available via the NASA software catalog at software.nasa.gov. And future versions of the Graham Suite will contain the re-architected and new Grahams. And the NASA SMD funding has been essential to addressing current limitations and accomplishing Graham developmental goals, as well as providing for the ongoing development, upgrades, and maintenance of the Grahams. Thank you again to the IPPW community for allowing us to present the latest advancements and releases that we have been able to do on the Grahams. Thanks. And the last slide is just the list of references if everybody wants to, look up the different papers that the models are based on.
Thank you, Hillary.
Thanks.
And we're coming now to our last speaker before we head to the Q&A for the talks and then the Q&A for the posters. Our speaker is Steve. He is a technical fellow at the Jet Propulsion Laboratory at Caltech. He has led the deployment of autonomy and artificial intelligence software for several missions, including Earth Observing 1, Mars Exploration Rovers, and the Rosetta Orbiter of ESA. He has been awarded 4 NASA medals for his work in artificial intelligence for space missions and is a 4-time honoree in the NASA Software of the Year competition. It's your turn.
Okay, great. Thank you very much. So I'm going to be talking about something completely different, onboard autonomy software that we're developing to explore options for the Europa lander mission concept. Next slide, please. So Europa lander is a very aggressive mission concept. It basically seeks to land on the surface of Europa and collect a number of samples and analyze them for potential biosignatures and communicate them back to Earth. We also have side goals of collecting seismographic data and panoramic imagery. I'm sure I didn't do any justice to the science goals, but since I'm not a scientist, you can just blame me for that. Next slide, please. This is a very challenging mission concept. We basically land with a finite amount of energy. And the challenge is that not only do we have this finite amount of energy, which, by the way, we can measure very inaccurately, we actually are greater than half of the time, we cannot communicate with the lander from Earth. So roughly, Europa is tightly locked to Jupiter, and basically when the sun is in view, the Earth is in view at that location. So it's less than 42 out of every 84 hours in that 3.5-day orbit that we can actually see the Earth. In addition, there's a round-trip flight time of about 2 hours. And the hardest thing is we have an unprecedented level of model uncertainty. The reason why we want to go there is we really don't know the terrain we're going to land in. We don't know the composition. We don't know how hard it's going to be to trench, how hard it's going to be to sample, and we really don't know what we're going to find. And so these challenges motivate the desire to have a higher level of autonomy. And we want to use the knowledge that we gain during the execution to drive the future planning. And I'm going to talk about 3 different levels of how we would do that. The first we call flexible execution. The next we would actually replan. And the last is we actually adjust from our prior experience. We adjust our model parameters into our future projections. Next slide, please. This is basically the task network that we have for the mission. And the good news is that we pretty much know everything that we want to do. The bad news is we really have very little idea how well each one of these will go. And so this task network has different parts to it. If we go to the next slide, please. There's basically a set of sampling chains where we try and choose a location, we trench, we actually successfully trench, we want to get down 10 centimeters, and then we sample. And then when we process that sample, we will analyze it in terms of doing a mass spec on it and different other tests. And anywhere in this chain, we could get stalled, or we could actually decide to terminate it because it's not promising. So like if the trenching takes too long, we might go to another site. If we process and do initial analysis and it's not an interesting sample, we might choose to terminate that early. And that's a significant amount of decision making that we want to do without the ground in the loop because that's very expensive and the clock is ticking. And also the communication of the data down takes a huge amount of the energy that we have because we have to communicate direct to Earth. And so we want to downlink summary products, and only if they're very interesting, downlink the exhaustive data products, particularly for the imagery and some of the other data sets that are quite large. Next slide, please. We also have on the side, we're going to be collecting this panoramic imagery data because you wouldn't go all the way to Europa and not have a camera. And then the seismographic and geophone data would also be of great interest. Next slide, please. So the way we model this, these goals and this mission is we actually have this network of activities that we do. And what we actually do is we actually search in the space of all of these concatenated networks for these different chains together. And we search for what we call the maximum utility network to the end of the mission. And we're constantly searching for that and reevaluating in the full autonomous capability. And so we have, think of it as a set of these different threads that we have, and we want to cram as many as possible of them as we can into the overall mission before we die. And we're constantly re-evaluating and reconsidering them. And the key important thing here is that you cannot get any value out of anything unless you get the data to the ground. It gives us no advantage to sample 20 times and not get the data to the ground unless you actually trust the system, the flight system, to sample 20 times and maybe deliver the best, 5 samples data to the ground, or maybe some other reduced summary products. And those are the things that we want to explore. Next slide, please. So within this, we have an autonomous system called MEXEC, which was originally designed for the Europa Clipper mission, and we're now adapting it to a number of other missions. We have these different grades of additional autonomy: flexible execution, replanning, and model parameter updates. Next slide, please. And so we're going to be talking about what we call none, or the traditional model of operations, and going up to these more and more aggressive models. Next slide, please. So the none strategy, or the static strategy, is what we do today. We actually uplink time-tagged commands, and if we fail on a resource or time overrun, something takes too long or something uses too much energy, we actually fail, and we wait until the ground is in the loop to upload a new sequence. The problem here is this requires significant margin. You might ask, well, why would we do something like this? Well, for example, this is the baseline currently used for the Mars Science Laboratory and the current mode of operations for the Mars 2020 Perseverance rover, and they do very short plans because they actually can typically uplink every Martian day or every Martian sol. And this is actually significant. By some metrics, they're leaving as much as 28% of the energy or time on the table. In other words, it's not being correctly used because you have to use this margin. Next slide. A flexible strategy is what we call the accordion on Mars 2020, which is what we're trying to move to, which is you have this linear set of tasks, particularly in sampling and robotic activities, but if one runs long, it has a deadline as long as it's allowed to run long until it hits some hard time bound. And so then you can have this sort of more flexible thing, but it's only flexible within, this chain that you can kind of push around. Next slide. The replan strategy is, again, flexible, but every now and then you take all of your future activities and you say, knowing what I know now, I'm going to reorganize the tasks that I'm going to throw into my network. And this is actually what we are intending and hoping to fly on Mars 2020. We have implemented this, and we're looking for approval to actually upload that. And the idea here is that you can take into account and vary where you're going to sample or how many samples you take, depending on your resource availability and when things take longer or shorter than you expect. And you can also switch to compressed data if you find out you have less energy than you thought. And then next slide, please. The last strategy is what we call the model update strategy. You do all of the above, except in addition, you actually change the parameters in your model. So if your trenching is taking longer than you thought, in the future, you expect it to take longer. If your trenching is using more energy than you thought because one of your actuators isn't performing, or more importantly, your power distribution unit is less efficient, your batteries are less efficient, or your uplink or downlink is less efficient, more likely your downlink, then you would take that into account when you project forward at your next replan. So this is even more, and this is something that is done typically on the ground endlessly with a parameter estimation for modeling, except we want to ship that on board the lander. Next slide, please. And so we've done a number of stochastic simulations with this. We have a model that we've developed that it's being used in some of the mission profiling. And as you might expect, these are the error bars, and the greens are the mean expected utility. As you might imagine, the expected utility is increasing as we allow the onboard autonomy to be more and more aggressive, and take into account this effectively, inferred or learned information as we get further and further on in the mission. Next slide, please.
2 minutes.
Yeah, and then just in conclusion, what we'd like to do in the future is right now we are reactive to off nominal performance. So what we do is we actually plan with our 100% predictive model, and then we react if things go badly, things take longer or take more energy, or the reverse, take advantage of things. We don't actually explicitly consider our uncertainty, and that's what we'd like to incorporate in the next version of this, which is really decision theory. Probability and utility is decision theory. And that's all I had. Thank you very much for your attention.
Thank you, Steve, and thanks to all of our speakers today. We're coming now to the Q&A for the talk, the second half. If there are any questions, feel free to post them in the chat. We had some discussions earlier already, so are there any questions about those?
Alena, maybe I can ask a question to Ben concerning these gravity poppers. Ben, you here? Yeah. Yeah, I was wondering, why did you exclude it, or what was the reason of kind of making the sensors unintelligent? Why not add in maybe a little bit extra communication capability on board and really try to kind of, I don't know, maybe exchange data or between the sensors or between these small nodes to get some more information?
Yeah, it's a good question. And the design of the probes is a real trade spectrum, right, from simplicity to complexity. And if you think about the systems engineering problem as having a certain mass allocation, you kind of have some trade-offs between numbers of probes and redundancy. And numbers of probes is valuable for spatial coverage as well as the potential high failure rates we may have from interacting with the surface. So we want to have, and we haven't precisely quantified that, but this architecture is by no means the ultimate balance in the proper balance in that trade space. I think we can look. I think there might be a lot of value in having the ranging links between the probes themselves. You get, some amazing scaling of your information when you have that kind of communication. I mean, our baseline does have an onboard radio to assist with synchronizing clocks, for example, and you could presumably pass small packets of information across that link. But we didn't look seriously into the radio hardware that would be required for interprobe communication. We wanted them not to be attitude controlled because that starts to ripple into a lot of subsystem requirements for attitude determination and control. So as conceived, I think the simplest we kind of found a local maxima in the let's say simple probe spectrum of that trade space. But I think having fewer CubeSats, for example, might also be an interesting study.
Yeah, because you can probably gain a lot of information if you just allow, for example, the distance measurement between the sensors.
Yeah, no, it's in some sense complementary to the angles measurement we get from optical sensors. It turns out you get pretty remarkable precision with appropriate centroiding techniques from angles only, and the fact that you don't constrain the range actually doesn't seem to affect the filter performance in terms of doing the orbit determination. So we did actually experiment with adding a ranging and Doppler constraint based on ultra-wideband radio ranging technologies, and it didn't seem to improve the gravity estimation performance much, but we didn't really do that for the interprobe communications.
Okay, good. Thanks a lot.
Okay, thanks. I have another question for Steve. Has there been any experiments across the drag or architecture that you were talking about for affected loads, or is it just
I'm not sure I could follow the question. The audio was breaking up a little bit. Could you please repeat it?
Yes, the question was, has the real experiment test tracking or capture for the expected levels?
I'm not sure, but I think the question was relating to like how we varied things in order to measure the expected utility. And so basically we took some very primitive models that we had for execution variation that we actually had adopted from Mars 2020, which was actually adopted from MSL models. But more recently, they actually have more interesting robotic models that talk about things like, there might be a crusty surface that would take a very long time to like penetrate, and then after that it might get easier, or maybe 4 centimeters down there might be crusty layer. And we're working to incorporate those more realistic and more interesting models. But I would say that the variation that we've done to date is extremely high level, and you can just think of it as, variation of basic parameters like energy, efficiency, duration of the task, and then random tasks failing that might be restarted. I hope that answers the question.
Yes, thank you. And there's another question in the chat for Benjamin. Can you assess the annual response and other granular material properties through your mission proposal?
Yeah, I was just about to respond to that in the chat. Yeah, it's an interesting question. There's a lot of, let's say, secondary investigations you might be able to do with this kind of swarm. We really focused on the gravity estimation, but there is information encoded in the bouncing on the surface itself, basically the dissipation factors from the collisions. You might be able to infer some crude measures of the surface structure, and from that, that's a very complicated question, and we didn't pursue that, but you could even instrument them. These probes could rest on the surface for longer periods of time, and if you could accommodate very simple instruments, the temperature sensor, the thermocouples maybe, you could get a lot of secondary science investigations.
Okay, thank you. Thanks to all your speakers again. We're handing over now to the Q&A for the cluster team.
Well, yes, I'm Manuel Dominguez. Please post the questions for the posters in the chat. We have prepared some of them.
Can you hear me?
Yes, certainly.
There is the question, what type of chemical sensors are you considering for odor tracking?
Yes.
Just take me a look. Christoph Waldmann, are you here? Okay, unfortunately, I cannot give you an exact answer to the type of science sensors we want to load to the Nano AOV, because this is currently under discussion, and that's more about the science team.
Okay, thank you very much. Let's see if there are more questions. I will also post them here. Question for Mr. Hasty. What do you think are the main challenges for in-space manufacturing of large-scale aerosols from the fabrication point of view?
Am I better to post the answer just to or sorry?
Sorry? Can you repeat?
I think there's a few kind of issues with from the manufacturing point of view, particularly with the example I've brought up with the foam manufacturing. The challenges in particular that we've kind of came across is to try and find materials, try and find how you would control the formation of materials like foams in a vacuum and in microgravity. And so there's kind of further investigation being done at the moment, looking into how we can control that process and how we can optimize the materials and the actual process to facilitate making those materials consistently. So that hope that answers some of the question.
Okay.
And obviously the other side of that as well would be to, even with the fantastic kind of packing ratio that I pointed to with in-space manufacturing, there's obviously still still limits in terms of the payload size and mass that could be reached with when supplied directly with feedstock from the ground. So I would say those are probably the kind of most significant challenges that we're looking at.
Okay, thank you. Then we have another question for Fuya Akiyama. It seems that the area shells would deploy well after atmospheric entry and would take some amount of time to fully extend. Have you performed trajectory simulations that take into account this in atmosphere deployment of the drag area?
Thank you for question. I haven't done any orbit simulation yet. As you said, it will take some time to deploy this air shell. And so we will work on that the future issue. Thank you for pointing this out.
Okay, thank you. Then we have a question for Dietrich. Can the tensegrity lander swim?
Yeah, so that's one of the concepts that we're investigating. One of the ideas we had is the rover is comprised of bars which are suspended in a network of cables. And the bars, we could have the cross-section, instead of being like a circular cross-section, it could have sort of like an elliptical cross-section, and it could use the flatter side as kind of like a paddle to paddle across the surface with possibly a buoyant payload. So that's one of the concepts we're investigating.
Okay, thank you. Then we have another question for Nitz. Is the propulsion system on the AUV inspired by nature?
No, currently we plan a system of 4 piezoelectric thrusters, 4 in the rear and 1 in the front. But to some point, we think yes, we plan to integrate fins in the hull. So up to some point, we could say yes, but not completely.
Okay, thank you very much. Then another question for Timons. What types of MEMS sensors are you considering, or sensors in general?
Is it also for the Triple project? Okay, for Timons, sorry.
Yes.
Yeah, so we could consider like a variety of sensors. These could be different on each temperature probe, but you could have things like temperature and pressure, maybe gravitometers. It's you could consider a suite of sensors available at that scale, and then any potential application that you would like to use the probes for, you could equip them with and deploy them for that.
Okay, so perhaps atmospheric science objectives, perhaps, or more focus on that?
Yeah, atmospheric science, maybe oceanography, studying vector fields, all these purposes.
Okay, thank you. Then we have a question for Rute. How do you deal with uncertainties in the augmented interfaces?
Yeah, that's a great question. Actually, for the predictive display, we didn't consider any uncertainty, but then when we performed the user study, we saw that this had a big impact on the performance of the participants, and especially their frustration, because they had losses of tractions, which of course brings a lot of uncertainty in the future trajectories of the rover. And when this happened, they were very frustrated with the interface, and then that's one of the reasons we think the results were not so good for the predictive display, but once we had semi-autonomy on board the rover, then the autonomy, since it was local, it could better deal with this uncertainty. So if there was some loss of traction, it deviated from the planned trajectory, it could immediately correct it. So this was the two approaches. Yeah, and in the future, what we think is that, of course, these predictions that we display on the screen should integrate this uncertainty. The question is then how can we display this uncertainty efficiently and in a user-friendly way? So that's still an open question.
Okay, thank you very much. Then another question for A. Galassi. Once anchored, do the gripping actuators consume power?
Hello. Yeah, so they don't. The linear actuator is non-back drivable when it's closed.
Okay, thank you. Well, any more questions for the poster?
Okay, well, if there are no more questions, I just wanted to say a quick thank you to everyone for participating today and for making the session a success. I'd like to remind everybody that the next session, Venus Exploration, is going to be held August 3rd, starting the same time as today. Thanks again.